Hello everyone. Now I would like to continue our discussion on additional properties of elements that show periodic trends. The two we're going to discuss now are electronegativity and electron affinity. Now every one of you should be familiar with the organization of elements, what we call it periodic table. On the periodic table you have the columns that are called families or groups. It's organized by similarity in chemical properties, and later on turns out is actually the organization of the valence, or organization of the electrons, particularly the valence electrons. Particularly this one's NS1, this one's NS2, and the list goes on. And now we're going to focusing on two of the many properties of the elements, and that exhibits the periodicity, the periodic repeats or periodic pattern for the value. It's the electronegativity and the electron affinity. So we're going to cover about the definitions and correlation between electronegativity, electron affinity, and the size. Again, I like to switch the mode into the silent movies, and I will show you a short animation sequence. Hope you enjoyed the short animation clip, and now we are understanding. Now you should understand the definitions for electronegativity and electron affinity. For electronegativity, and electronegativity is a measure of the strength of attraction between the neutral atom and the free electron. And the electron affinity measures the amount of the energy that is going to be released when a neutral atom captures a free electron. Now, all those two parameters are intimately related to the size of the atom, As the size of the atom getting smaller, the attraction between the nucleus and the valence electrons getting stronger, and hence the overall atom will have a stronger attraction for the free electron, hence higher electronegativity, and also by the same token will release more energy when it actually acquires a free electron, hence higher electron affinity. As we all can see, those repeated trends of the atomic radius across, going from the top of each group down to the bottom, and in this case it's group 1 elements, the alkaline metal plus the hydrogen alkaline metal. This is the hydrogen, those are the alkaline metals. You can see the size increases, and the size increases from the top to the bottom for each group of family. And if we're looking at across each period, size decreases. And then if you can take the logical argument from the animation sequence coupled with the trends in the atomic radius, you probably can quickly draw the conclusion that we will have decreased electronegativity from the top to the bottom of the group as the size is getting bigger, and the electronegativity will be increasing across the same period due to decreased sizes. So then let's check whether that's the case. And here's the plot for electronegativity of elements, and we will also, this time we're going to switch to the dynamic periodic table, as we showed before, contains multitude of very, very useful information. In this case, the electronegativity is highlighted for the properties, As we can see from top of the column, for hydrogen, electronegativity 2.2, and quickly drop down to 0.98, 0.93, 0.82, 0.82, 0.79, and 0.7. And in general trend, it is decreasing from top to the bottom of the same group. You can take a look at on the same group, the group 2 now, the alkaline earth metals. In this case, it's 1.57, 1.31, 1.0, 0.95, 0.89, and 0.9. And also interestingly, you can looking at the halogens. You're looking at the fluorine 3.98, extremely high. Chlorine 3.16, 2.96, 2.66, and 2.2 respectively. And now let's take a look at across the same period. If you look at the period 2, lithium at 0.98, 1.57, 2.04, 2.55, 3.04, 3.44, and 3.98. A nice, very nicely interesting increasing due to the size getting smaller. One of the very interesting features we're going to have here, I want to point it out, is the electronegativity values for the noble gases. As you can see here, the helium, neon, and argon do not have any value for a very simple reason. As you can recall, for those noble gas elements, they are very happy with their electron configurations. It was called the octet rule. If you already achieved the noble gas electron configuration, specifically for helium, neon, and argon, do not want to have any additional electron. So it has no intention to trying to gain another electron. So in practicality, there's no electronegativity for helium, neon, or argon. However, the situation getting a little bit more complicated, as we do have a very strong electronegativity value assigned to the krypton and the xenon, and those are for the reasons that's not going to be covered in this class, but I do want to point it out, and there's an interesting feature here. And as you can notice, as from the top to the bottom, for each group, the electronegativity decreases. From the left to the right, of the same period, the electronegativity generally increases, and increases quite significantly. Be careful about the noble gases. And in general, when we discuss about electronegativity, we put them aside and do not discuss them, because the first three, extremely stable, they do not want to gain any additional electrons. So then it's kind of confirmed with those trends we just pointed out. And now let's take a look at the value being plotted here for the this is period 1, this is period 2, period 3, and very nice, very tight trends for electronegativity. Situation gets a little bit more complicated when we get to the period 4 and the D block elements, which give the situation a little bit more a little bit more complex and complicated, but it's not going to be covered in this first year chemistry class. You will learn later in high-level chemistry classes. So this is another nice block, and this is what's being plotted on here is electronegativity versus the atomic number for the major S and P blocks. Remember, you have group 1, 2 as the S block, group 13 to 18 as the P block. So this is group 1, and this is period 1, this is period 2, and this is period 3, and this is period 4, 5, 6, and 7. So those. Oh, my mistake. So this is period 1, and this is period 2, and that will be period 3, and that'll be period 4. Yeah, actually, I was correct, but you can't see those trends, and it's very nice, and it's very much periodic. Very much periodic. So in general, the general overall approach when we answer questions regarding electronegativity and also electron affinity, remember they go hand in hand. Higher electronegativity, higher electron affinity. If you got any problem ranking those elements in terms of the electronegativity, you gotta first understand the problem, and then you identify the trends in size, and then you use that to correlate with electronegativity and electron affinity. Essentially, larger the size, the lower the electronegativity and lower the electron affinity. Now let's take a look at a problem. We got it from last time, and in this case we need to change the question a bit. So instead of the first ionization energy, we're going to ask about we're going to ask about the following elements in terms of increasing in, let's see, electronegativity. Okay, electronegativity. And in this case, same analysis of the problem. We're looking at increasing, so which means from the smallest to the biggest electronegativity, from smallest to the biggest electronegativity. And we're also looking at this one is the electronegativity, and we want to looking at from the lowest to the highest. and because of the correlation between electronegativity and the size. So now we're actually looking for from the largest to the smallest size. And now we're coming back to that, how we rank those elements in terms of size. And you will know cesium is greater, it's bigger than rubidium. Rubidium is greater, it's bigger than potassium, because of the effect number one. This is all in group one. The number of rings, the number of principal energy level increases, so the size increases significantly. And now you're looking at between potassium and calcium. They're on the same period, but calcium has more protons, so effect number two dominates, and the calcium will have smaller size than potassium. And now we switch over to the group 2 now. Magnesium is on top of calcium, has one less principal energy level, so it's smaller than that. So hence the cesium has the, we have to change that now. Cesium has the lowest electronegativity. Rubidium have the second lowest, potassium have the third lowest, calcium have fourth lowest, and magnesium have the fifth lowest. In this case, it turns out it has the highest electronegativity. Now I'll ask a question very similar to the ask in the last section. Which element on the periodic table has the lowest electronegativity and electron affinity? And as we said before, we talked about the general trends, and this is increasing due to decreasing in size. This is actually decreasing due to increasing in size. So the element that has the lowest electroaffinity will be in this region. Let's change the color. Will be in this region, and one has the highest will be in this region. It turns out the answer for that, for the lowest electronegativity, then we'll have cesium. Also for the electron affinity, it will be the same trend. Which one has the highest? That will be fluorine. That will be the fluorine. Cesium and the fluorine. So with that, let's recap what you learned, what we discussed today. So it's the electronegativity and the electron affinity. Make sure you actually understand the definition of those two. Electron negativity measures the ability or the strength of a neutral atom attracts a free electron. So it's higher electronegativity, stronger or easier for you to gain an electron. So the electron affinity is associated with the amount of energy released by the neutral atom when it gains the electron. It's stronger the electronegativity, the larger amount of energy will release. So the higher electron affinity. Both of those parameters correlates very well with the size of the element, size of the atom. Smaller size, stronger electronegativity, higher electron affinity. And with that, go and check on the worksheets and solve those problems accordingly, according to the general approach, the steps outlined in this podcast. Thank you very much for your attention.